math and beats. This video, we're going to do it. We are going to generalize the power rule. Let's go. All right, so what we're going to do here is we're going to try to show this. We're going to try to show that the derivative of a power function where the exponent is any real number n is what we might think it is. Let's see. Let's assume, for the sake of this situation, that we're dealing with positive values of x. And let's assume the number b is a real number, any real number. Then, as we've shown in previous videos, I can rewrite x to the b as e to the b times ln x on that exponent, right? And again, that's because that is the same as e to the ln x power to the b power, and e to the ln x power is x, so hence we get x to the b, okay? Now, having said that, we can then find the derivative of x to the b, keeping in mind that b is just any real number here. Well, that's the same thing as the derivative of e to the b times ln x power. By the chain rule, because of course we have established that when you take e to the power of x, differentiate it, we know the derivative is e to the x. So if I have e to the function of x like we have here, chain rule tells us we gotta take the derivative of that power, which is the derivative with respect to x of b times ln x, times e to that functional power b times ln x. The derivative of ln x has been established. That is 1 over x, and hence what do we get? We get b divided by x times e to the power of b times ln x. But of course, e to the power of b times ln x is just x to the b. And right here, if we simplify, x to the b divided by x is x to the b minus 1. And look what we get. B times x to the b minus 1, keeping in mind that b is any real number here. And thus what this shows is what we have maybe been thinking all along, the general power rule. And we could do a similar proof, of course, if x is less than 0 as well. And there you go. The general power rule, differentiate x to the n with respect to x, where n is any real number n. And what do we get? N times x to the n minus 1. Of course, we had previously established that for all rational numbers n, but now we extend it. All rational and irrational numbers n, meaning any real number n. So there we go. It works. And just to do a couple of quick examples here in this video, what if we were to ask to find the derivative of x to the negative pi with respect to x? Well, negative pi is a real number. And so we just apply the power rule, bring down that exponent, negative pi, times x to the negative pi minus 1 power. The end. Power rule, power rule. How about if we were asked to find the derivative of cosine of 2x to the e power with respect to x? Well, this is a chain rule, of course. That's the same as the derivative with respect to x of 2x to the e power times the derivative of the cosine function, negative sine of that stuff, 2x to the e power. And then apply the power rule to the 2x to the e. I'm going to take that negative sign out in front too. So negative 2, bring down the power of e, times x, e to the power of e minus 1, and then times sine of 2x to the e power. There you go. See? Real number exponents on the power rules. It works. Finally, in this example here, how about let's differentiate the tangent of t to the power of root 2, all inside the root with respect to t. So we can think of this as the derivative with respect to t of tangent of t to the root 2 power, all of that to the 1/2 power because it's inside the root. So we got multiple chain rule here. First, we'll apply the chain rule to that half power and get a 1/2 times tangent of t to the root 2 power, all of that to the negative 1/2 power. So there's a general power rule at work. But then, of course, we have to multiply that with the derivative with respect to t of the tangent of t to the root 2 power. And so keep going here. This is another chain rule right there, right? And so we're going to write this as a 1/2 tangent of t to the root 2 power, all to the negative 1/2 power. Then I'm going to have to take the derivative with respect to t of t to the root 2, derivative of that inner function. The derivative of the tangent function is the secant squared function, and leave the input alone. So secant squared of t to the root 2 power. Finally, after differentiating t to the root 2 power, that's another power rule. So bring down the root 2. We get a root 2 over 2 times tangent of t to the root 2 power, all to the negative 1/2. And then I got to multiply that with t to the root 2 minus 1 power. Power rule right there. All times secant squared of t to the root 2 power. And if we really wanted to, we could take that tangent of t to the root 2, all quantity to the negative 1/2, and I'll write it over, the square root in the denominator. But we'll just leave it like so in this one. Why not? And there we go. Very short video here to establish the general power rule for all powers that are real. Any real power, it works. And we looked at a few quick examples here. And this, of course, can be done now because we've established some other things like derivatives of logarithms. So that's why we talk about it. That's it. We're done with this video. Next video, we're going to look at a process called logarithmic differentiation. Very fun. Until then, it is Matt Bates. I'm out of here.